how to draw the shear force bending moment diagrams for various examples. In this rest of the chapter 6, what we'll see is we will try to apply that calculated moment in calculated moment to calculate the stress. So let's see that. We make it slightly. Now, consider an example. For instance, let's take a beam and let's apply a moment. Let's say this side is fixed. What happens? Obviously, this bends like that, right? It would bend up. Maybe let me redraw it again. That's what happens when we apply moment M. Let's observe this carefully. Meaning, if we take a beam, you apply a moment, what happens on this fixed edge? You have a moment reaction. The moment reaction is also M. So, due to this effect, the beam would become like that, isn't it? This is how we are bending. So the applied moment is causing bending like this, isn't it? So if you observe carefully, what is happening to the top surface? This one here. And what is happening to the bottom surface? The bottom surface is being stretched. Hope the spelling is correct. The top surface is being compressed. Do you agree to that? The top surface is being compressed, the bottom surface is being stretched. Or isn't the beam acting as if you have a compressive loading on the top, but you have a tensile loading on the bottom, right? Isn't it acting as if there is a compressive loading, normal compressive, but this is normal tension, normal tension. Isn't it acting like that? Right? So the top part is being compressed, the bottom part is being stretched. That is what is happening when we apply moment. Right? Because of this, the top part is slightly being compressed inside, the bottom part is being stretched. I'm just exaggerating the picture here. So assuming that there is this line or there is a plane inside the beam which we call neutral, where it is not being stretched, neither being compressed. Its final and initial lengths are the same. We call that neutral axis. That means in this picture, there is a neutral axis somewhere here. We call that neutral axis. Right? We're trying to set up the problem. We're trying to set up the concept so we can apply the concept in situations where we have moment. That is what is shown on the slides here. There is a neutral surface. Other assumptions we need to consider when we apply the theory is plane sections remain plane. They'll not become curved. They'll not be bent. Plane will remain plane. Length of longitudinal axis remains unchanged. That means this length, that remains unchanged. For example, if there is loading which is causing too much change in the length, we can't apply the theory that we will be using in this class. Then plane sections remain perpendicular to the longitudinal axis. If this is the longitudinal axis, that is the longitudinal axis. The plane sections, that means the section is when you slice it. The sections are always perpendicular to the longitudinal axis. So in this case here, this is the neutral or longitudinal axis, right? Yeah, that is the longitudinal axis. So the planes at every cross section, they're perpendicular to the longitudinal axis. In plane, distortion of section is negligible. So if there is any distortion in the plane, we will not consider that. We need a special theory to discuss all those cases. So we will apply or we'll develop a concept that is having these assumptions, taking these assumptions into account. Now, we will develop something called a flexural formula. This flexural formula is something that will give a relation between stress and moment, saying my over I is negative my over I. As a quick process to, you know, how this theory was developed, how this theory was developed. Like I said, when we apply moment onto a beam like this is a moment. We can consider as if, let me draw this slightly bigger. We can consider as if there is this compressive force, and from the neutral axis, there is, so let's say this is the neutral axis. From the neutral axis, we are applying the tensile loading. That means here we are trying to stretch, and here we're trying to compress, right? So this application of loading, that application of loading is being treated as certain force acting into, right? This is acting into and certain force acting out of it, isn't it? So we converted moment to an equivalent force that is being applied at certain distance away from neutral axis. So what is the concept of moment? Isn't moment force times perpendicular distance? So to get this moment here, to get that moment, there should be certain amount of force acting away from neutral axis at certain distance, right? And because this force is not constant at all locations, so here the force is smaller, but at the edge the force is larger. Again, here near to the neutral axis the force is smaller, but at the edge the force is larger. Because of this, what we need to do is we have to say moment, we have to say, we say moment is some y times df. Df means we take a small strip. So this is 2 o'clock. So let me try it in black. We take a small strip. This is a small strip. We take a small strip and we say that small strip is df force, a small amount of. So the force acting on that strip, this strip, that strip, the force acting on that strip, and the distance of that strip away from the neutral axis is y. Typically in all the courses, in majority of courses, we assume going up is positive, right? So if you're going down, that means if you're measuring this force, you're going negative, just letting you know. So always top is positive y. So moment is nothing but this y times df, right? And df, we can write df. What is force in terms of stress? Isn't it sigma times dA? So can we write moment as integral y times y times um y times sigma times dA, right? And can be written as the maximum, sigma can be written in terms of maximum stress. So there can be a relation between sigma and sigma max. Where does sigma max occur? Because force is larger here, assuming it's uniform cross section, force is larger on the edge. Isn't sigma max bigger on the edge, right? Or here, right? On the edges. So sigma at any y, that means sigma as a function of y. Y is the y coordinate. So at different y's, you have different sigmas where the sigma here is bigger, sigma here is larger. That means farther away from neutral axis, you have a higher normal stress when there is bending moment. So this being y, what I'm trying to write is sigma as a function of y can be written in terms of sigma max, where sigma max is occurring on the edges. And it can be written as sigma max times y over c, where c is the radius. So this is c. Or you can write it as r. Radius is r. You can either write it as r or you can either write it as c. So if you plug in y to be positive number, because if you go from here to that direction, it is y is positive y, right? When you go from here to negative, what happens? It's a negative y direction. So if you apply y to be positive c, right? Because this is also c, that is also the bar to the bottom is also c. What happens when you plug in y equal to positive c? You get, when you apply sigma at c, what do you get? You get sigma max, right? Because when you substitute y equal to c and c on the numerator and denominator, they both cancel out and you get sigma max. But are you supposed to get sigma max or negative sigma max when you apply positive c? Because when you apply positive c, isn't it in compression here? Is it, isn't it being compressed here? That means shouldn't you get negative? That is why to have this to have this in place, what we write is we write the formula to be this. Stress at any y is negative sigma max times y over c. For example, now when we want to find what is the stress at this point, we will substitute y to be negative c because we're going down, and when we go down, it's a negative y. So when you apply negative c, what do you get here? Negative and the negative here, they both get cancelled and you get positive sigma max. So that is why we add this negative as a correction factor. So let's substitute this into this formula. So m is equal to integral y times sigma is negative sigma max times y over c times dA. So which is, so because sigma max is a constant, we write it outside the integral. Even c is a constant, it's the radius of the material. We write this outside the integral. So we write it as sigma max over c integral y square dA. From mathematics, what is y square dA? We call this area moment of inertia, which is moment, hence can be written as, which is represented as I, is negative sigma max over c times I. So sigma max is negative m times c over I, right? So this is the maximum sigma. So what is sigma as a function of y then? We should use this, we should use this formula, which is sigma as a function of y is nothing but negative sigma max, which is negative of negative mc over I times y over c. So we get sigma as a function of y is my over I. Agreed? And that's exactly what we have here. Sigma is my over I. And you have to also remember the positive representation. Positive representation is whenever you take on the left hand side, moment has to go clock, on the right hand side counterclock. This is the positive representation. Shear going down on the right hand side, shear going up on the left hand side. That's the positive representation. So in our case, we had the positive representation incorporated, right? So when we have sigma f, we wrote it as some df times y, and we got the form. So typically, like I said, when we, because on the in the positive representation, the top side would be negative and the bottom side would be positive, because here it's being compressed, here it's being elongated. We always use a sigma y, we use a correction factor, negative my over I. So we write this negative as a correction factor. So this negative here as the correction factor. Okay. So With that, what we can do is we can apply this formula, and that's exactly what we see. Sigma is negative my over I. We can apply this formula to solve some problems. That means if I give you moment, that means if I give you a beam and I say, hey, you know what, there is a moment acting here. Can you tell me what is the stress occurring at this point or this point? What will you do? Stress acting at that point, sigma, let's call it A, B. Sigma A is moment, negative moment times, because what is the formula? Sigma is negative my over I. So times, what is y? Y is the distance from the neutral axis to the point. So where is the neutral axis? It's always at the centroid in this case. When we're talking about curved beams, it's a different story, but in this case, neutral axis is at the centroid. So what is y in this case? Y is nothing but this distance. That distance is y. So my over, what is I? I is area moment of inertia or second moment of inertia. There are different names. So so it is integral y squared dA. We don't need to apply integral always. We have a table and we have some known geometries. For example, for this shape, what is the moment of inertia with respect to that axis? Let's call this xx axis. What is the moment of inertia with respect to ixx? Is if you know B, if you know H, it is BH cube over 12. The formula is, you don't need to remember the formulas because I will give you the formulas, but you need to know how to apply the formulas. Listen to this important thing. Moment of inertia with respect to different axes is different. For example, moment of inertia of this shape with respect to xx is bh cube over 12. But what is moment of inertia of the same shape with respect to that axis, yy? Assuming this is still B, this is H. Moment of inertia of YY axis is, can you tell me, looking at this, is it the same? No, it is not the same. Moment of inertia with respect to YY axis is HB cube over 12. So the cube is being applied to something that is perpendicular to the axis of consideration. Isn't B here perpendicular to Y? That's why we have a cube to that. Isn't H here perpendicular to X? That's why there's a cube to H. So this is a common formula for rectangular shapes. What is the moment of inertia for a triangular shape? I'm going to give you that. What is the moment of inertia for a circular shape with respect to that axis? I'll give you that. What you need to understand is, in this formula, when you apply I, you're taking moment of inertia with respect to the axis of rotation. So, so when you're applying, so take this as an important point. When you say sigma is negative my over I, What is M? Bending moment at that cross section. What is Y? Distance of the point, distance of the point of consideration on the cross section from neutral axis. Right? Y is the distance of the point from the neutral axis. That means different points on the same cross section can have different stress. So what is I? That is the critical thing that you need to understand. I is we call this area moment of inertia. It is area moment of inertia of the cross section with respect to the axis of rotation. Or with respect to the, you can also say this, or you could also say this as with respect to the axis to which, with respect to the axis to which the bending moment let me explain this to you, because majority confusion is about I. Which I should you take? That's the majority confusion. For example, let me give you a bar that looks like this. Okay, let me give you a bar that looks like this. Now let me give the axis. This is X. Okay, this is Y, and that is Z. So, okay, now I'm going to apply a bending moment like that. Let's say on this side it's fixed. Now tell me, the bending moment is applied with respect to which axis? Think in your mind. Is the bending moment applied with respect to x-axis, or is it applied with respect to z-axis, or is it applied with respect to y-axis? For example, let me shift the axis here. This is z, this is y, and that is x. Bending moment is applied with respect to which axis? Bending moment is applied with respect to y-axis in this case, isn't it? So isn't it being applied like that? So you're trying to rotate this beam, or you're trying to bend the beam with respect to y-axis, isn't it? So this is my, correct? Though I gave you m, it is the moment with respect to y-axis. So According to the definition given here, area moment of inertia of the cross section is with respect to the axis of rotation, or with respect to the axis which bending moment is applied. The bending moment is applied with respect to which axis? My. So I is going to be you have to find the moment of inertia of this cross section with respect to y, because the moment is applied with respect to y. So in any problem, it is critical for you to first of all visualize with respect to which axis is the moment being applied. Then you have to find out moment of inertia with respect to that axis. That is very, 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 very important. Okay. Now, look at the picture on the left. Think and think, I'm going to tell you the answer in a little while. With respect to which axis is the moment applied here? Is the moment applied with respect to X, Y, or Z? Observe this picture on the left. For example, here, maybe this is better. The moment is applied with respect to which axis in this case here? It is applied with respect to Z, isn't it? The moment is applied with respect to this axis. You're applying a moment like that, isn't it? And what is this axis? This axis is nothing but Z. Okay, that is something that you have to observe before you apply this formula. This is called flexural formula. Enough of the theory. Let's do a problem. How about that? This problem will be slightly complicated. I'm starting with the complicated problem itself, but let's do it. We can all do this together. Okay, so this is a problem in the textbook. This is example 6.12. So let's do this example. Read the question. You have this beam. You have this beam on which there is a distributed load of 5 kilonewton per meter applied. There's a pin joint on the left and there's a roller on the right. The question is, determine the absolute maximum bending stress in the beam. Draw the stress distribution over the cross section. What is the stress at point B? So there are three questions. Question number 1, question number 2, question number 3. Determine the absolute maximum bending stress. Do you know what is a maximum bending stress? We know that, isn't it? We know that the maximum bending stress is this, right? My over I, where you replace y with the outermost radius, isn't it? You would all say yes, but if the cross section is circular, yes, you would just replace y with the outermost radius. But if the cross section is I, what will you do? The cross section is I, and if this is the neutral axis, what is the outermost point? So what is the meaning of y here? When you apply sigma is equal to my over I, which is negative because the top is positive. So what is y? It is the, and if you want sigma max, negative m times c over I. What is c? C is the outer. I wouldn't say, you shouldn't say outer. I have to say farthest point from neutral axis. What is the farthest point from the neutral axis? Isn't this point here? Or basically, isn't every point on that surface the farthest point? Every point on this surface the farthest point? So by looking at this, can you tell me what is the value of C? Can you tell me what is the value of C in meters? Isn't it 150 mm plus 20 mm? Because this is 150 and from here to there is 20. So isn't it 170 mm? Or isn't it 0.17 meter? Yes, C is 0.17 meter. So the C is 0.17 meter. What is M? Because look at this carefully. We are asking for maximum bending stress. That means M should be maximum bending moment. Where is the maximum bending moment in the beam? For that, to find that, we have to draw bending moment diagram. And luckily, your bending moment diagram was given. But even if it's not given, you should be able to draw. And didn't we draw a similar problem by assuming W in place of 5 in the previous exactly here in the previous video? We use W. Isn't this W? Isn't this and that look the same? You're applying a distributed load W, then what is the maximum bending moment? So you have to follow all of this approach. You may ask me, is there a better way? There are some graphical ways you can Google, you can learn, you can follow the textbook, but this would be the most accurate way to do, which I presented here. It's up to you. The point is it's WL square over 8. What is W? In our case, it's 5. So 5 times 6 square over 8. How much do you get? 5 times, I'm doing my calculator. I have my calculator here. 5 times 6 square over 8. I got 22.5. And it is occurring at L over 2, which is occurring at 3. So you have to develop your ability to draw bending moment diagrams, because in the exam I will not be giving you this picture. You have to draw this. This is the bending moment diagram. So the M max here, M max is 22.5 kilonewton times meter. Okay, so you know M, you know C. What about I? What is the moment of inertia? What is the moment of inertia of, what is I, by the way? Do you know the definition? Do you still remember the definition of I? I is area moment of inertia of the cross section. So for this one, this is the cross section, right? Let me draw straight. If you make a cut, that's the cross. When you make a cut, your cross section looks like this. Your cross section looks like this when you make a cut. This is the cross section. So what is the area moment of inertia of the I cross section with respect to the neutral axis? And where is the neutral axis? It is given in this problem. Due to symmetry, neutral axis in this case is at the centroid. And where is the centroid? Because of symmetry, it is symmetric with in the vertical axis, it's symmetric with respect to the horizontal axis. So obviously it will be exactly at the center, right? So with respect to the neutral axis, you have to find the moment of inertia. This is a concept from statics. How many of you still remember? I'll do this problem for you. I'll help you understand the problem, but the next problem you should be able to develop your ability to find I. Okay, okay, now let's do this. So in the textbook, if you have if you have a beam like this with, like I said, this is B, dimensions are this is H, then what is given is with respect to X axis, moment of inertia, area moment of inertia with respect to X axis is BH cube over 12. That is given to us. That is given to us. And we have to also remember one other concept, which is what is the area moment of inertia of the same bar B, and let's say this is H, with respect to that axis, with respect to, let's say, let's take some axis like that, with respect to an axis like that. So the axis need not be on the beam. The axis need not be on the section of interest. It can be away from the section of interest. So let's say I give you that this distance is x. Then if I ask you the question, what is I with respect to some arbitrary axis x dash, x dash. So what is I x dash, x dash? There is a way we can still find that. It is defined with parallel axis theorem. Remember that because we need it a lot in this course. According to parallel axis theorem, we can calculate the moment of inertia with respect to an axis away from the centroidal axis. Let's call this xx. And that is nothing but moment of inertia with respect to the centroidal axis plus area of the element times square of the distance between axis and centroidal axis. So this is the axis, this is the centroidal axis. So if we have to calculate moment of inertia with respect to an axis that is not passing through the centroidal axis, we can still find the moment of inertia by this parallel axis theorem, which is moment of inertia with respect to the centroidal axis plus area of the element times square of the distance between the axis and the centroidal axis. Now tell me, what is Ixx? We know that, right? It is nothing but BH cube over 12 plus what is area of this element? Isn't it B times H times what is the distance between? So this is basically called the D. What is the distance between the axis and the centroidal axis? How much is that? Isn't it, if the total height is h, isn't it h over 2? So what is the distance? Isn't it h over 2 plus x square? Because this is the square of the distance between the two axes. So this is the moment of inertia with respect to x dash x dash. We need this concept. Make sure you understand this concept. Okay. So using this idea, let's apply and find the moment of inertia of this I cross section. Let's calculate the moment of inertia of that I cross section. What I'll do is I'll paste the picture here so I can easily draw it. Oops. Where did I paste it? Copy, paste. Okay, there you go. Let's find the moment of inertia for this axis. For a moment of inertia of this cross section with respect to the neutral axis where it is this axis. Okay, let's do this. That means we have to find I with respect to NA, neutral axis. Or I'm not going to write A, I'll just write it as N, UIN. I'll just leave it as I. Is, how much is it? We have to take three different sections. This is section number 1. This is going to be section number 2, and this will be 3. So I is nothing but moment of inertia I1 plus moment of inertia of I2 plus moment of inertia of I3 with respect to the neutral axis, right? So moment of inertia of the first shape with respect to neutral axis plus moment of inertia of the second shape with respect to neutral axis, moment of inertia of the third shape with respect to neutral axis. How much is this one? The first shape. The neutral axis passes through the centroidal axis of the first one. So it will be nothing but bh cube over 12. So I1n, where how much is b? Isn't it that? And isn't that given as 20? So it is going to be 0.02 times how much is height? This is the height, and the height is 150 plus 150 is 300 mm, so it's going to be 0.3 cube bh cube or 12. That is the moment of inertia of the first shape. What is the moment of inertia of the second shape? This is the second shape. So we moment of inertia of the second shape with respect to the neutral axis. Moment of inertia of the second shape with respect to the neutral axis. So neutral axis is here and the second shape is here. We have to apply parallel axis theorem. So tell me what is the moment of inertia of the second shape with its neutral axis or with its centroidal axis. How much is that? With respect to this, it's going to be bh cube over 12. With respect to that, you have to add this number with area of the element times square of the distance between the centroid and the centroid and the neutral axis. So it is BH cube over 12 plus area times D square. What is B with respect to this axis? B will be this. And how much is that? 250. So it's going to be 0.25 meter. H cube, what is the height? This is the height. Always, like I said, height is always perpendicular to the centroidal axis. So in this case, it's going to be 20 mm. So it's going to be 0.02 cube over 12 plus what is the area of the element? Isn't it 20? 0.02 times 0.02 times 250. 250 is 0.25, right? Isn't this the area? 0.02 times 0.25. That's the area times what is the distance between. So what is the D? What is the distance between the centroid of this to this? Isn't it 150 plus half of 20? Because that is 20, right? Maybe there are too many things there. Isn't it 150 plus, because we want the distance from that axis, we need that distance. How much is that distance? Isn't it 10? So 150 plus 10 is 160. So it is 0.16 square. That is the that is the moment of inertia of the second shape. What is the moment of inertia of the third shape with respect to neutral axis? Due to symmetry, 3 is exactly looking same as 2. So we will just write I to n, right? So how much is this? Take your calculators. Take your calculators and then do this. 0.02 times 0.3 cube divided by 12 0.02 times 0.02 times 0.3 cube divided by 12. I got 4.5 times 10 power minus 5. For this one is 0.25 times 0.02 cube divided by 12 plus 0.02 times 0.25 times 0.16 square. I got this to be 1.28 times 10 power minus 4, and this should also be the same as 1.28 times 10 power minus 4 units, meter to the power of 4, meter to the power of 4, meter to the power of 4. Add all the three numbers and tell me how much is I. We should get the 4.5. So no, answer is this times 2 plus 4.5 times 10 power minus 5. I got 3.01333 so on times 10 power minus 4 meter to the power of 4. Right? That's what I got here. That is the moment of inertia of this. Are we done with the problem? No, we are not done with the problem. We have to calculate the first one. Determine the maximum bending stress. Now tell me what is the maximum bending stress? Maximum bending stress, sigma max, is m negative m times farthest distance over I, because we want magnitude, either compression or tension. And this point or that point, both are the same distance away from neutral axis. We can take either of them. But you have to remember, in the positive representation, the bottommost point will be in tension, the topmost point will be in compression. So this would be in compression, that would be in tension. So it's going to be M, which is 22.5 kilonewton meter. So I'm going to write as 10 power 3 Newton meter times what is the farthest distance from the neutral axis to the point. So what is this distance? How much is that? Isn't it 0.15 plus 0.02? Isn't it 0.15 plus 0.02 over I 3.013 10 power minus 4? This is meter and this is going to be meter. So we should get meter would cancel with meter square on the bottom. So we have to get the maximum bending stress is, right, the maximum bending stress is, let's do this, 22.5 times 10 power 3. There are a lot of things, so calculation, we shouldn't make calc error. We have to be very, very careful. Plus 0.02 divided with 3.013 times 10 power minus 4. We have 0.1269, I'm going to write 7 Newton per meter square. No, I did a calculator. I got 0.12. Oh, I forgot to divide with 10 power minus 4. Got you. So I got, oh, no. I got 126. I'm going to put some dot. 1, 2, 3, 4, 5, 6. I got 12.69 times 10 power 6 Newton per meter square. That's what I got when I solved this number, and which we can write it as 12.69. I can write it to 7 mega, and this is Pascal. So megapascal is sigma max. That's the exact answer we need to get here. You got it there. Now, draw the stress distribution. The number one point is done. How would you draw the stress distribution? That means if we were to draw the I cross section somehow, right? And this is the I cross section. How will you draw the stress distribution? On the top, what will happen? Is that in tension or compression? If you listen to this lecture carefully, it's in compression. If this is how the moment is acting, on the top is compression, on the bottom is tension. Exactly on the neutral axis, what happens to the stress on the neutral axis? Or what is the value of stress? Apply the formula. Momentum times y. What is y? Y is the distance from the neutral axis to the point of concentration. Where is the point? On the neutral axis. That means y is 0. That means you get stress to be 0 on neutral axis. That means This is how the stress distribution is, right? That's how the stress distribution is. So draw the stress distribution of the cross section. Yeah, this is the stress distribution of the cross section, where this is 12.7 megapascal and this is also 12.7 megapascal. Last thing, what is the stress at point B? Where is B? B is here. What is the stress at B? Apply the formula. M, I, they remain the same. I does not change for every point. Every point on the cross section will have the same I. What about M? It'll be the same. What about Y? Y is the one that will change. Y is the distance from the neutral axis to B, which is 0.15. So just apply the formula and write it as to 0.15. So what I get, if I do that in the calculator, I got, if I do sigma at B is negative my over I. Negative m is 22.5 10 power 3. Y is, because from the neutral axis we're going up, right? We're going up. So this is where B is. This is where B is. So we're going from the neutral axis, we're going up. So I'm going to write positive Y, and Y will be how much? 0.15 meter over I will be the same value we got on the top, 3.3, 3.013 10 power minus 4 meter to the power 4. This is Newton meter. Then I got 11, 1, 2, 3, 4, 5, 6, 11.201, 11.2 megapascals is what I got for sigma B. Oh, I'm sorry, negative. Okay, that's how we do the problem. And that's exactly the answer. So try to understand this stuff. Take a moment, pause, solve the problem, check the problem. So that means when you're applying moment with respect to this axis, you took moment of inertia with respect to that axis. What if I'm applying a moment like this? That means it is being rotated with respect to it is being rotated with respect to that axis, right? That means we need to take moment of inertia with respect to whatever that axis name is for this whole I cross section. So it depends. Are we applying moment like this, or are we applying a moment like that? We have to observe carefully. Okay. So next question. There is a beam, cross-sectional area. The beam shown in 6.27 has a cross-sectional area of a channel, and the cross-sectional area is given like this. So let me select this. Let me select this cross-section area. Oh, I can select here. Hmm. I can select this anyways. So this is the cross section area given. I'm going to draw the cross section. I think that's the most easiest way to do it. So the cross section looks like this. It looks like hmm. The cross section looks like this. And the dimensions given are this is 20 mm. This is 15 mm. And this is 250 mm. Okay. Then the question is, if this is how the cross section is, the question asks you, due to this loading, what is the maximum bending stress? So the question is, what is sigma max? That's the question. What is sigma max? How will you find it? What's your idea? No matter what, no matter what, sigma max formula, that will remain negative my over I, where this is not y, but you says this is c, where c is the maximum distance away from the neutral axis, and m is the maximum bending moment with respect to the neutral axis. First of all, we have to find where is the neutral axis, then we can go from there. So for this cross section shown, where is the neutral axis? Is it symmetric with respect to horizontal? No, it is not. Is it symmetric with respect to vertical? Yes, it is. That means the neutral axis, that means it will lie somewhere on this. The centroid lies somewhere on this point. We need to find the centroid pretty much. Is it that point, this point, this point, that point? We have to find it. How do you find the centroid? We find the centroid by sigma, because we need to find the y bar, right? Y tilde A over sigma A. From statics again, how many shapes do you have? Let's call the shape number 1. Let's call the shape number 2. Let's call the shape number 3. Then you write y1 a1, y2 a2, y3 a3 over a1 plus a2 plus a3. What is y1? Oh, these are all tildes. Tilde is from the distance of the centroid of part 1 from a reference line. We have to take a reference line. Let's take you know let's take this to be our reference line. With respect to this line, with respect to that reference line, where is the centroid of the first shape? I think I have to give you the length. Oh, it's 200. I forgot to give you the length. This is, okay. Now tell me, where is the centroid of the first shape? Centroid of the first shape, somewhere here. That is, how much is that? That will be 100 mm, right? So let's write it. That implies this is 100 mm. So let's leave everything in mm. I'm not going to convert to meters, so I'll get answer in millimeters. What is A1? Isn't it 15 times 200? Because I want the area of this. So this is the width and that is the height. I'm going to get area of that. Plus, what is y2a2? It's the same. Y2 is, it looks exactly the same with respect to the reference line as the first shape. So it's 100 times 15 times 200 plus y3 is, how much is y3? Where is the centroid of third shape? That is the centroid. And how much is the distance of the centroid from the reference line? That is 10 times A3 is 20 times 250, right? 20 times 250 over area 1. What is area 1? 15 times 200. What is area 2? 15 times 200. What is area 3? 20 times 250. Do this in the calculator with me. I'm going to do it. You also do it with me. Okay, so when we plug in, we get, I'm going to plug in that 100 times 15 times 200 times 2 plus 10 times 20 times 250 divided with 15 times 200 times 2 plus 20 times 250. I got 59.09 millimeter. This is y bar. That means the centroid lies on this line, but at a distance of but at a distance of 59.09 it lies at a distance of 59.09 from the reference line. So this is where the centroid is, or to be specific, this is where the neutral axis is for the system. Now I'm going to erase the reference line. We don't need it any longer. So this is the neutral axis. Okay. Then that means when you look at this problem, the shape is like that, isn't it? this is how the shape is, and we are applying bending moment like that. That means we are applying bending moment. No, we're not applying bending moment like that, right? We're applying bending moment like this, isn't it? Because given in the picture that there is a 2.6 kilonewton with a slope 12, 5, and 13. That means due to this, what is the moment reaction? Because you have a moment reaction due to the application of that force. And how much is the moment reaction? And the moment is being applied, if you observe carefully for the problem, moment is applied with respect to that neutral axis. This is what you should be able to imagine looking at the problem. Because in the problem here, you were given like this. Can you tell me the cross-sectional area or the shape of the cross-sectional area by looking at this picture? No, you can't. We have to look at this picture. So when I combine this cross-section area with this, technically almost close, this is how we get. So tell me, what is the moment? How do you calculate the moment? Because it's an equilibrium, you say sigma moment with respect to, let's call this point A, with respect to A is equal to 0, implies we assume this moment is clock, so I'm going to write negative m, and how about this 2.6 kilonewtons? 2.6 kilonewtons, I can resolve this into that and into this. So this is going to be 2.6 times 12 over 13 kilonewtons, and this will be 2.6 times 5 over 13, because we need to give some axis. So the axis, let's call this z, let's call this x, let's call this to be y. So we are rotating with respect to x-axis, right? In this case, the rotation is with respect to x-axis. So by looking at it, tell me the moment due to the 2.6 kilonewtons. The 2.6 kilonewtons in the y component is 2.6 in the y, no, along this negative z, I'm sorry, 2.6 times 12 over 13. That's the force times what is the distance of the 2.6 times 12 over 13, which is this line, from A. Is the length given? Isn't it 3? Or no, the question is determine the maximum bending stress occurs in the beam at section AA. At AA. Now, this is A. 2.6 times 12 over 13 is this force. What is the distance between this and that? Isn't it 2? That means, isn't this distance 2 meters? That means, don't we have this to be times 2? And is it clock or a counterclock? With respect to A, it is counterclock because it rotates like this with respect to A, the 2.6 kilonewton force. That means I'm going to write it to be positive. Remember, we also have this y component of the force, given force, which is this force, 2.6 times 5 over 13, and it is acting on the top edge. What is the distance between that and A? What is this distance? Isn't that distance, isn't this distance 59 mm? That's exactly what we just found out, right? That means we have to, in addition to this, we have to write, and by the way, this gives a moment like that, which is counterclock again. That means we get 2.6 times 5 over 13 times that 0, this one converted to meters will be 0.059, right? I'll just write it till there, 909, and that should be equal to 0. That implies what is the moment? Isn't the moment 2.6 times 12 over 13 times 2 plus 2.6 times 5 over 13 times 0.05909? That implies the moment that is being applied is, if you calculate this, we should get 4.859 kilonewton times meter. Do this. Now we're not done. We calculated the moment, but we have to calculate the maximum. So we calculated the moment to be 4.859 kilonewton meter. To calculate the moment, we had to calculate the component of the force, and we needed to calculate the distance, which is which is this distance. And to calculate this, we had to calculate the centroid, right? See, everything is interlinked, and we are still not done because we have to calculate I, moment of inertia. How do we calculate moment of inertia? I. So for this cross section, how many shapes do we have? We have 1, we have 2, and we have 3. So what is the moment of inertia I? According to the concept we discussed before, the moment of inertia I is moment of inertia of the first shape with respect to the neutral, moment of inertia of the second shape with respect to the neutral, plus moment of inertia of the third shape with respect to the neutral, which is, tell me the first shape. What is the moment of inertia of the first shape with respect to the neutral axis? If you know first shape with respect to neutral, second will almost be the same. Not almost, it will be exactly the same because they both look like the same with respect to the neutral axis. So, can you tell me that? How many of you are thinking, oh, it's the moment of inertia I1, it's looking like a rectangle. So you may be thinking, oh, is it nothing but BH cube over 12 I1? How many of you are thinking that? Or if you have something else, do you think we have to use parallel axis theorem? When should we use parallel axis theorem? When the neutral axis, where this is the neutral axis, does not coincide with the centroidal axis of 1, then we have to apply parallel axis theorem. That means in this case, we have to apply, or should we not apply? Is neutral axis of the system, of the entire cross section, the same as the centroidal axis of 1? Where is the centroidal axis of 1? It is at the centroidal axis of 1 is this. This is the centroidal axis of 1. This is at 100 mm from the topmost surface, right? But where is the neutral axis? Neutral axis is 59.09 mm from the top. So is the centroidal axis of 1 the same as the neutral axis of the cross section? Because neutral axis of the cross section passes through the centroid of the cross section, not centroid of 1. Centroid of 1 is different from centroid of the cross section. That means we need to apply parallel axis theorem with this to be D, with that to be D. So apply parallel axis theorem. So what I'll do is I will just erase this part because I know you've already taken that. And I want to write I1. What is moment of inertia of the first shape with respect to neutral axis is BH cube over 12. This is with respect to the centroidal axis of 1 plus you have to apply parallel axis theorem AD square, which is what is B with respect to this. B would be this, which is 15. I'll write everything in meters. So 0.015 times H is 0.2 cube over 12 plus area is 15, 0.015 times what? 200, 0.2, right? Area is 15 times 2 BH cube over 12 plus 15.2 times what is the distance? What is this D? This is 59.09. The total is 100. From here to there is 100. So what is D? Isn't D 100 minus 59.09? Isn't this 100 minus 59.09? And this should be converted to meter, so this should be 10 power minus 3. And because it's a D square, I have to square this. That is the moment of inertia of the first shape with respect to the neutral axis. Moment of inertia of the second shape with respect to neutral axis is same as moment of inertia of first shape with neutral axis, because 2 and 1 look like the same with respect to the neutral axis. What is I3? Moment of inertia of the third shape with respect to neutral axis is moment of inertia of third shape is its centroid is here. This is the centroidal axis of the third shape, right? So BH cube over 12, which is, what is B? Isn't it 0.25? What is H? Isn't it 0.2? 0.02. BH cube over 12 plus area. This is area. 0.02, 0.25 times 0.02 times H cube, sorry, D square. which is, how much is d squared? That means what is this distance? The total is 59.09, and that is 10. This is 10. That is 59.09. How much is this? The total minus 10. The total is 59.09 minus 10, and this is to be converted to meter, and that is to be squared. So the total, the moment of inertia I is I1n plus I2n plus I3n. Let's do this. Take your calculators. Don't be lazy. Do this problem. Do the calculation, because you should be, this is mechanics of materials course. It's a lot of steps, a lot of calculations. There is no other option for you to do this. There's no other option. You have to do this. Times 0.02 times, I'm also doing it. So 100 minus 59.09, so 0.1 minus 0.05909 squared. Got the first one to be 1 point, or let me write it here, 1.5 10 power minus 5 meter to the power 4. So I2n will be the same. I3n is 0.25 times 0.02 cube divided by 12 plus 0.25 times 0.02 times 0.04909 squared. I got this to be 0.22 10 to the minus 5 meter per 4. So the total is 0.5 times 2 plus 1.22 times 10 power minus 5. I got 4.22 times 10 power minus 5 meter to the power 4. That is the moment of inertia for the shape. Hence, we will apply that and write it as 4.22 times 10 power minus 5 meter to the power 4. So maximum bending stress, sigma max, at the cross section AA. AA means this is the cross section here. What I mean to say is, so the cross section is that. The cross section AA is my over I. It's a negative, but m is negative because you see on the right hand side we have to always assume it's going counterclock. But is it going counterclock? No, it is not. It's going clock, so we should write negative there. Negative times negative 4.859 kilonewton meter, so 10 power 3 times y. You have to write the point that is farthest from, so because we anyways want the magnitude, we want the magnitude So what I'll write it as is m, because anyways we are writing magnitude, the negatives don't matter anymore. 4.859 times 10 power 3, because it's a kilonewton, we're writing it as newton meter, times y. Which point is farthest from the neutral axis? Is this point farthest from neutral axis, or is that point farthest? This point is at a distance 59 millimeter. How about the distance from neutral axis to that point? Isn't it 200 minus 59? Isn't it 140.91? Isn't this 140.91 millimeter? So if you were to write that, you will write this as 140 is going to be 0.14091 meter over I is going to be 4.22 times 10 power minus 5 meter to the power of 4, which is going to be 16.2 megapascals. And you see, at this point, moment is going from here to there, right? The direction of moment. That means this point is in compression, that point is in tension. So here, that's why we have write this is compressive. So the maximum stress is this much, and that is a compressive stress. What is the tensile stress? The maximum tensile stress. You have to substitute in place of this, we will write 59.09 millimeter. Then we will get the maximum tensile stress which is acting at that point. Okay. So this is the idea. You have one more problem that you have to see in 6.14. This is also pretty interesting problem. So please also look at this example problem. And with this, so I'll only have up to 6.4, section 6.4 for the homework or for the exam. Okay. So this is the point till which you should be thorough, you should be proficient. I'll upload homework and quizzes soon, and watch out for the emails from me. All right. Be safe and all the best. Bye bye.